But the reality is, like, 2 bits, 3 bits, 4 bits aren't very useful in the real world, because even with 3 bits, you can count to 7. With 4, you can count to 15. These aren't very big numbers, so it tends to be more common to actually use units of measure of 8 bits at a time. A byte is just that. 1 byte is 8 bits. So if you've ever used the vernacular of kilobytes, megabytes, gigabytes, that's just referring to some number of bits, but 8 of them together compose one individual byte. So here, for instance, is a byte worth of bits, 8 of them total. I've added all the additional placeholders. And what number does this represent in decimal, even though you're looking at 8 binary digits? It's just 0, because like literally every column is a 0. Now this is a bit more of mental math, but unless you know it already, what if I change all of the zeros to ones? I turn all 8 light bulbs on. What number is this? Yeah, so 255. Now, those of you who didn't get that instantly, that's fine. You could certainly do the math manually. I dare say some of you have some prior knowledge of how to do this sort of system. But 255 means that if you start counting at 0 and you go all the way up to 255, OK, that's 256 total possibilities once you include 0 in the total number of patterns of zeros and ones. And this is just going to be one of these common numbers in computer science. 256, why? Because it's referring to 8 of something. 2 to the 8 gives you 256. And so you're going to commonly see certain values like that. 256, back in the day, computers could only show 256 colors on the screen. Certain graphics formats nowadays that you might download can only use as many as 256 colors because, as we'll see, they're only using, for instance, 8 bits. And therefore, they can only represent so many colors of the rainbow as a result. So this then is how we might go from just zeros and ones, electricity inside of a computer, to storing actual numbers with which we're familiar. And honestly, we can go higher than 255. What do you need to count higher than 255? A 9th bit, a 10th bit, an 11th bit, and so forth. And it turns out common conventions nowadays, and we'll see this in code too, is to use as many as 32 bits at a time. So that's a good chunk of bits. And anyone want to ballpark how high you can count if you've got 32 bits available to you? Oh, fewer people now. Yeah, in the back. Yeah, so it's roughly 4 billion. And it's technically 2 billion if you also want to represent negative numbers, but we'll revisit that question. But 2 to the 32nd power is roughly 4 billion. However, nowadays it's even more common with the Macs and PCs you might have on your laps and even your phones nowadays to use 64 bits, which is a big enough number that I'm not even sure offhand how to pronounce it. That's a lot of permutations. That's 2 to the 64 possible permutations, but that's increasingly commonplace. And as an aside, just to dovetail things with our discussion of AI, among the reasons that we're living through over these past few years, especially this crazy, interesting time of AI, is because computers have been getting so much faster, exponentially so over time. They have so much more memory available to them. There's so much data out there on the internet in particular to train these models that it's an interesting confluence of hardware now actually meeting the mathematics and statistics that we'll talk about later in the class that ultimately make tools like the cat we just built possible. But of course, computers are not all math. And in fact, we'll use very little math per se in this class. And so let's move away pretty quickly from just zeros and ones and talk about letters of the alphabet, say in English. Here is the letter A. Suppose you want to use this letter in an email, a text message, or any other program. What is the computer doing underneath the hood? How can the computer store a capital letter A in English if at the end of the day, all the computer has access to is a source of electricity from the wall or from a battery, and it has a lot of switches that it can turn on and off and treat the electricity in units of 8 or 32 or 64 or whatever? How might a computer represent a letter A? Yeah, we need to give it an identity, so to speak, as an integer. In other words, at the end of the day, if your entire canvas, so to speak, consists only of zeros and ones, like that is going to be the answer to every question today. You only have zeros and ones as the solution to these problems. We just need to agree what pattern of zeros and ones, and therefore what integer, what number, shall be used to represent the letter A. And hopefully, when we look at that pattern of zeros and ones in the right context, we'll indeed see it as an A. So if we look inside of a computer, so to speak, in the context of like a text messaging program or a word processor or anything like that, that pattern shall be interpreted, hopefully, as a capital letter A. But if I open up Mac OS's or Windows or my phone's calculator program, I would want that same pattern of zeros and ones to be interpreted instead as a number. If I open up Photoshop, as we'll soon see, I want that same pattern of zeros and ones to be interpreted as a color, presumably, not to mention videos and sound and so forth, but it's all just zeros and ones. And so even though I, when writing that chat program a few minutes ago, didn't have to worry about telling the computer, oh, this is text, this is a number, this is something else, we'll see as we write code ourselves that you as the programmer will have control over telling the computer how to treat some pattern of zeros and ones, telling it this is a number, this is a color, this is a letter, or something else. How do we represent the letter A? Well, it turns out a bunch of humans in a room years ago decided, this pattern of zeros and ones shall be known globally as a capital letter English A. What is that number if you do the quick mental math? So indeed, 65, because we had a 1 in the 64's place and a 1 in the 1's place. So 65, that's just sort of it. It would have been nice if it were just the number 1 or maybe the number 0. But at least after the capital letter A, they kept things consistent, such that if you want to represent a letter B, it's going to be 66. Capital letter C, it's going to be 67. Why? Because the humans in this room, a bunch of Americans at the time, standardized on what's called ASCII, the American Standard Code for Information Interchange. Doesn't matter what the acronym represents, but it was just a mapping. Someone on a piece of paper essentially started writing down letters of the alphabet and corresponding numbers so that computers subsequently could all speak that same standard representation. And here's an excerpt thereof. In this case, we're seeing 7 bits worth, but eventually we ended up using 8 bits in total to represent letters. And some of these are fairly cryptic, maybe more on those another time. But down here, if we highlight just one column, we'll see that indeed, on this cheat sheet, 65 is capital A, 66 is B, 67 is C, and so forth. So why don't we do a little exercise here? What pattern of zeros and ones do I see here? I've got 3 bytes, so 3 sets of 8 bits. And even though there's no placeholders now over the columns, what is this number? It's 60. Yeah, so we got the 1s, 2s, 4s, 8s, 16, 32, 64's column. So indeed, this is going to be the number 72. 72. This is not what computer scientists spend their day doing. This is just to reinforce what it is we just looked at. And I'll spoil it. The rest of these numbers are 72, 73, 33. And anyone in this room could have done that if you took out a piece of paper, figured out what the columns are, and just do a bit of quick or mental or written math. But this is to say, suppose that you just got a text message or an email that if you had the ability to look underneath the hood of the computer and see what pattern of zeros and ones did you just receive over the internet, suppose that pattern of zeros and ones was 3 bytes of bits, which, when you do the math, are the numbers 72, 73, 33. Well, here's the cheat sheet again. What message did you just get? Yeah, so it's high. Why? Because 72 is H and 73 is I. Now, some of you said hi fairly emphatically. Why? Well, 33, turns out, and you wouldn't know this unless you looked it up or someone told you, is an exclamation point. So literally, if you were to text someone like right now, if you haven't already, HI exclamation point in all caps, you would essentially be sending 3 bytes of information somehow over the internet to that recipient. And because their phone similarly understands ASCII, because it was programmed years ago to do so, it knows to show you HI exclamation point and not a number, 3 numbers no less, or colors, or something else altogether. So here we then have high, 3 digits in a row here. What else is worth noting here? Well, there's some fun sort of trivia embedded even in this cheat sheet. So here again is A, B, C, D, E, F, G, and so forth, 65 on down. Let me just highlight over here the lowercase letters, 97, 98, 99, and so forth. If I go back and forth, does anyone notice the consistent pattern between these two? Yeah, so the lowercase letters are 32 away from the uppercase letters. Well, how do we know that? Well, 97 minus 65 is, 32. 98 minus 66 is, 32. And that pattern continues. What does this mean? Well, computers know how to do this. Most normal humans don't need this information. But what it means is if you are representing in binary with your transistors on and off representing some pattern, and this is the pattern representing capital letter A, which is why we have a 1 in the 64's place and a 1 in the 1's place, how does a computer go about lowercasing this same letter? Yeah. Perfect. All the computer has to do is change this 1 bit in the 32's place to a 1, because that has the effect mathematically, per our discussion, of adding the number 32 to whatever it is. So it turns out you can force text from uppercase to lowercase or back by just changing a single bit inside of that pattern of 8 bits in total. All right, why don't we maybe reinforce this with another quick exercise? We have an opportunity perhaps here for maybe to give you some stress balls right at the very start of class. Could we get 8 volunteers to come up on stage, maybe over here and over here and over here on the left. Let me go all the way on the right. Let's see. OK, the high hand here, the hand that's highest there. Yes, we're making eye contact. How about all the way? Wait, let's see. Let's go here in the crimson sweatshirt here. And how about in the white shirt here? Come on up. Did I count correctly? Let's see. Come on down, the 8 of you. I didn't count right, did I? 1, 2, 3, 4, 5, 6. It's ironic that I'm not counting correctly. 8 here. How about on the left in gray? OK. Oh, and OK. In black here. Come on down. All right, hopefully this is 8. 1, 2, 3, 4, 5, 6, 7. 7? I'm pretty sure. OK, 8. There we go. All right. So let's go ahead and do the following exercise. I've got some sheets of paper pre-printed here. If each of you indeed want to do exactly what you're doing and line up from left to right, each of you is going to represent a placeholder, essentially. So we have over here the ones place, all the way over here. And then we have the twos place, and the fours place, and the 8s, 16, 32, 64, 128. And we come bearing a microphone. If each of you want to say a quick hello, your name, maybe your dorm or house, and something besides computer science that you're studying or want to.
Hi, that's loud. OK. I'm Allison. I'm a freshman in Matthews. And I like climbing. And I'm thinking of CS and econ.
Number 2.
Hi, I'm Lily. I'm in Hurlbut this year, and I'm thinking of doing CS and government.
Nice to meet.
Hi, I'm Sean. I'm in Candidate Hall, and I'm thinking of doing astrophysics and CS.
Welcome.
Hi, I'm Jordan. I'm doing applied math with a specialization in CS and econ. And I'm in Wigglesworth, and I like going to the gym.
OK, nice. 16.
Hi, I'm Shiv. I'm studying Mackey, and I'm in Candidate G.
Nice.
Hi, I'm Sophia. I'm in Thayer, and I'm thinking of doing electrical engineering.
Welcome.
Hi, my name is Marie, and I'm in Candidate B, and I really like CS, physics, and astrophysics.
Hi, I'm Alyssa. I'm in Holworthy. I'm also thinking of studying math or physics, and I also like to climb.
Nice. Welcome to you all. So on the backs of their sheets of paper, they have a little cheat sheet that's describing what they should do in each of 3 rounds. We're going to spell out together a 3-letter word. You all, as the audience, have a cheat sheet above you that represents numbers, 2 letters. These folks don't necessarily know what they're spelling. They only know what they individually are spelling. So if your sheet of paper tells you to represent a 0 in a given round, just kind of stand there awkwardly, no hands up. But if you're told on your sheet of paper to represent a 1, just raise a single hand to make obvious to the audience that you're representing a 1 and not a 0. And the goal here is to figure out what we are spelling using this system called ASCII. All right, round 1, execute. What number is this here? I'm hearing, you can just shout it out. What number? 66 or B. So you're spelling B. All right, hands down. Round 2. More math. Feel free to shout it out. Oh, I heard it. Yeah, 79, which is O. OK, so we have B, O. Hands down. 3rd and final round. Execute. Number? Yes, 87, which is the letter? W, which spells? Bow, if you want to take your bow now. OK, here we go. You guys can keep those. OK, thank you. All right, you guys can head back. Thank you to our volunteers here. Very nicely done. We indeed spelled out bow. And that's just because we all standardized on representing information in exactly the same way, which is why when you type B-O-W on your phone or your computer, the recipient sees the exact same thing. But what's noteworthy in this discussion is that you can't spell a huge number of words. Like, yeah, English, OK, we've got that covered. But odds are you're noticing, depending on your own background, what human languages you read or speak yourself, that a whole bunch of symbols might be missing from your keyboard. For instance, we have accented characters here. In a lot of Asian languages, there's so many more glyphs than we could have even fit in that cheat sheet of numbers and letters. And so ASCII is not the only system that the world uses. It was one of the earliest, but we've moved on in modern times to a superset of ASCII that's generally known as Unicode. And Unicode uses so many more bits than ASCII that we even have room for all of these little things that we seem to send constantly nowadays. These are obviously images that you might send with your phone or your computer, but they're technically characters. They're technically just patterns of zeros and ones that have similarly been standardized around the world to look a certain way, but this is an emoji keyboard in the sense that you're sending characters. You're not sending images per se. The characters are displayed as images, obviously, but really these are just like characters in a different font, and that font happens to be very colorful and graphical as well. So Unicode, instead of using just 7 or 8 bits, which if you do the quick mental math, if ASCII only used 7 or let's say 8 bits, how many possible characters can you represent in ASCII alone? 256, because if we do that quick mental math, 2 to the 8th, 256 possibilities, like that's it. That's enough for English, because you can cram all the uppercase letters, the lowercase letters, the numbers, and a whole bunch of punctuation as well. But it's not enough for certain other punctuation symbols, not to mention many other human languages. And so the Unicode Consortium, its charge in life has been to come up with a digital representation of all human language, past, present, and hopefully future, by using not just 7 or 8 bits, but maybe 16 bits per character, 24 bits, or heck, even 32 bits per character. And per before, if you've got as many as 32 bits available to you, you can represent, what, like 4 billion characters in total. And that's just one of the reasons why these emoji have kind of exploded in popularity and availability. There's just so many darn patterns. Like, what else are we going to do with all of these zeros and ones? But more importantly, emoji have been designed to really represent people and places and things and emotions in a way that transcends human language. But even then, they're somewhat open to interpretation. In fact, here's a pattern of, I think, 32 zeros and ones. I'm guessing no one's going to do the quick mental math here, but this represents what decimal number, if we do in fact do out the math, with that being the ones place all the way over to the left? Well, that's the number 4,036,991,106. Who knows what that is? It's not A, and it's nothing near A, uppercase or lowercase, but it is among the most popular emoji that you might send typically on your phone, laptop, or other device, namely this thing here, face with tears of joy, which odds are you've sent or received recently. But interestingly, even though many of you might have iPhones and see and send the same image, you'll notice that if you see a friend who's got Android or some other device, maybe you're using Meta's Messenger program or Telegram or some other messaging service, sometimes these emoji look a little bit different. Why? Because what a Unicode has done is they decided there shall exist an emoji known as, face with tears of joy. Then Apple and Google and Microsoft and others, they're sort of free to interpret that as they see fit. So what you see on the screen here is a recent version from iOS, Apple's operating system. Google's version of the same looks a little something like this. And on Telegram, if you have animations enabled, the same idea, face with tears of joy, is actually animated. But it's the same pattern of zeros and ones in each case. But again, they each essentially have different graphical fonts to present to you what each of those images actually is. All right, so those are each, images. So those are each images. How is the computer representing them, though? At the end of the day, we've represented numbers, we've represented letters, but how about these things here, colors? So how do we represent red or green or blue, not to mention every other color in between? At the end of the day, we only have one canvas at our disposal. Yeah. So integers is the exact same answer as before. We just need to agree on what number do we use for red, what do we use for green, what do we use for blue, and we can come up with some standardized pattern for this. In fact, one of the most common techniques for doing this, and one of the most common ways to do this in the real world, is to use a combination of 3 colors together. Some amount of red, some amount of green, and some amount of blue, and mix them together to get most any color of the rainbow that you might want. This is sort of a picture of something I grew up with back in the day, where in like middle school when we'd watch movies or some kind of show in class, we would kind of, this projector screen would be over here. This is an old school projector with 3 different lenses, one of which projects some amount of green, some amount of red, some amount of blue. And so long as the lenses are correctly oriented to all point at the same circle or like rectangular region on the screen, you would see any number of colors coming to life in the old school video. I still remember all these years later, we would kind of sit and lean up against it because it was super warm and you could feel it. It was an easy way to fall asleep back in grade school. But we use the same fundamental color system nowadays as well, including in modern programs like Photoshop. So let's abstract that away, focus on just 3 colors, some amount of red, green, and blue. And let's propose for the sake of discussion that we want to mix together like a medium amount of red, a medium amount of green, and just a little bit of blue. For instance, let's propose that we'll use 72 amount of red, 73 amount of green, or 33 amount of blue, RGB. Now, why these numbers? Well, in the context of ASCII, or Unicode, which is just a superset thereof, what does this spell? High. But again, if you were instead to open a file containing these 3 numbers, or really these 3 bytes of bits in Photoshop, you would hope that they're going to be interpreted not as letters on the screen, but as the color of a dot on the screen instead. So it turns out that typically, when you have 3 of these numbers together, each of them is using a single byte, so 8 bits. So you can have 0 red or 255 red, 0 green or 255 green, or 0 to 255 of blue. So 0 is none, 255 is the max. So if we mix these together, imagine just like that projector consolidating these 3 colors into one central point. Anyone want to guess what you're going to get if you mix some red, some green, some blue in those amounts and way back? Yeah, you're going to get a dark shade of yellow. I've brightened it up a little bit for the projector here, but you're going to get roughly this shade of yellow. And we could play with these numbers all day long and get similar results if we want to represent different colors as well. And indeed, whether it's Photoshop or some other program, you can actually combine these amounts in all sorts of ratios to get different colors. So if you had 0, 0, 0, so no red, no green, no blue, take a guess as to what color that's going to be in the computer. So it's going to be black, like the absence of all 3 of those colors. But if you mix the maximal amount of each of those, 255 red and green and blue, that's going to give you white. Now, if any of you have made web pages before or used programs like Photoshop, you might have seen numbers like 00 or FF. Long story short, that's just another base system for representing numbers between 0 and 255 as well. But we'll come back to that mid-semester when we make some of our own filters in sort of an Instagram-like way, manipulating images of our own. So where are these colors coming from, or where can we actually see them? Well, here's just a picture of that same emoji, face with tears of joy. If I kind of zoom in on that, and maybe zoom in again, you can start to see, if you blow it up enough, or if you put your eyes close enough to the device sometimes, you can actually see individual dots or squares. These are generally known as pixels, and they're just the individual dots that collectively compose an image, which is to say that if each of these dots, which is part of the image, is going to be a distinct color, like this one's yellow, this one's brown, and then there's a bunch in between, well, you're using some number of bits to represent each of those pixels' colors. So if you imagine using the RGB system, that's 8 plus 8 plus 8 bits, so that's 24 bits, or 3 bytes, just to keep track of the color of each and every one of these dots. So now if you think about having downloaded a GIF at some point, a PNG file, a JPEG, or any other file format, it's usually measured in what file size? Like megabytes, typically. That means millions of bytes. Why? Because if it's a pretty big photograph or pretty big image, each of those dots takes up at least 3 bytes, it would seem. And if you do out the math, if you've got thousands of dots, each of which uses 3 bytes, you're going to quickly get to megabytes, if not even larger, for things like, say, videos. But again, it's just patterns of zeros and ones, and so long as the programmer knows what they're doing and tells the computer how to interpret those zeros and ones, and equivalently, so long as the software knows, look at these zeros and ones and interpret them as numbers or letters or colors, we should see what we intended to represent. All right, so that's colors and images. What about how many of you kind of played with these little flip books as a kid where they've got like 100 different little pictures and you flip through them really quickly and you see what looks like animation in book form? Well, this is essentially a video. So therefore, what is a video, or how can you think of what a video is? It's just a whole bunch of like images flying across the screen, either on paper or digitally nowadays on your phone or your laptop. And that's kind of nice because we're sort of composing more interesting media now based on these lower level building blocks. And this is going to be thematic. We literally started with zeros and ones. We worked our way up to letters. We then worked our way up to sort of images and colors and thus images. Now we're up at this level of hierarchy in terms of video. Because what's a video? It's like 30 images per second flying across the screen, or maybe slightly fewer than that, that collectively tricks our mind into thinking we are seeing motion pictures. And that's the old school term for movies, but it literally is what it was. Motion pictures was this film was showing you 30 pictures per second, and it looks like motion, even though you're just looking at images, much like this flip book, very quickly, one after the other. What about music? Well, how could you go about representing musical notes if, again, your only ingredients are zeros and ones? Even if you're not a musician, how do you represent music like that on the screen here? Yeah? OK, so the frequency, like the tone that you're actually hearing from the device, what else might weigh in besides the frequency of the note? Yeah? So the speed of the note, or maybe the duration, like if you think about a physical piano, like how long you're holding the key down for or not. What else? So the amplitude, maybe how loud, like how hard did you hit the keyboard to generate that sound? So let me propose, at the risk of simplifying, we could represent each of these notes using 3 numbers, maybe 0 to 255 or some other range that represents the frequency or the pitch of the note, the duration, and the loudness. And so long as the person receiving a file containing all of those zeros and ones knows how to interpret them 3 at a time, I bet you could share a musical file with someone else that they could hear in exactly the same way that you yourself intended. Let me pause here to see if there's any questions now, because we've already built our way up from zeros and ones now to video and sound. Yeah, in front.
How does the computer know to differentiate between what the letter like 65 would be and then what the number 65 is?
So how does the computer distinguish between the letter 65 and the number 65? It's context dependent. So put simply, and we'll see this as early as next week, the programmer tells the computer how to display the information either as a number or a letter, or equivalently, once programmed, the software knows that when it opens a .gif file or .jpeg or something else, to interpret those zeros and ones as colors instead of as like .docx for a Microsoft Word file or the like. Other questions on any of these representations? Yeah, in front.
Can we go over like the base 10, base 2 thing like really briefly? I didn't know that.
Sure, so can we go over base 10 and base 2? So base 10 is like literally the numbers you and I use every day. It's base 10 in the sense that you have 10 digits at your disposal, 0 through 9, and any numbers you want to represent in the real world must be composed using 0 through 9. The binary system, or base 2, is fundamentally the same. It's just the computer doesn't have access to 2 through 9. It only has access to 0 and 1. But much like the light bulbs I was displaying here, you can simply ascribe different weights to each of the digits so that instead of it being as much as the ones place, the tens place, and the hundreds place, if we more modestly say the ones place, the twos place, the fours place, we can use the same system. In binary, you might need to use more digits to count as high, because in 255, you can just write 255. That's 3 digits in decimal. But in binary, we've seen you need to use 8 such digits, which is more, but it's still much better than unary, which would have had 255 light bulbs on instead.
And is binary and base 2 like the same thing?
Is binary and base 2 the same thing? Yes. Just like base 10 and decimal are the same thing as well, and unary and base 1 are the same thing as well. All right, so let me just stipulate that even though we sort of took this tour quickly, at the end of the day, computers only have zeros and ones at their disposal. So again, the answer to any question as to how can we represent X is going to somehow involve permuting those zeros and ones into patterns, or equivalently into the numbers that they represent.